My name is Aaron Binet. I am teaching cybersecurity for over 16 years in high schools and universities, and I want to introduce you to my new Understanding Cybersecurity series on Udemy. This series is intended for every student, beginner or advanced, taking his steps into the cybersecurity world. It covers 5 distinct courses: Network Fundamentals, The Power of Wireshark, TCP/IP and Beyond, Network Programming, and putting everything in action with web protocols. This series is focusing on the understanding of cybersecurity, getting the know-how and the hands-on experience so that you can pave your way to success in cybersecurity. This video, IP addressing, is one of the 26 videos available on the third course, now available for a limited time on a considerable promotion on Udemy. The third course covers IP addressing and routing, ICMP error management and forensics, a detailed walkthrough of all TCP algorithms, network hazards and their defense, and a higher level protocol assessment, including DNS, HTTP, and the cryptographic versions of HTTPS and beyond. Enjoy this IP addressing video, and I invite you to enroll to the substantial course on Udemy. Good luck. We have noticed the class-based addressing as providing a solution for the early times where there are not that many companies or IP addresses given away. The idea was that class-based addressing used an 8-bit boundary to define those classes. Accordingly, we could have only class A's of 256 companies with 60 million each, or class B with only 16,000 companies with 65,000 each, or class C with 2 million companies or households with 256 computers each. But what if we only needed 1 million and not 16 million computers for a class A company? In that perspective, by getting that address of, let's say, 34 something something something, we would waste 15 million computers. And if we needed a company with, let's say, 300 computers, we would have to use up one of the class B addresses rather than the class C addresses, even though we are not that far away from the 256 boundaries. That lack of flexibility created a situation of wasting IP addresses and not being able to serve that many addresses that were needed. That created the need for a much more flexible approach called classless addressing, which is used today. Classless addresses uses boundaries which are not fixed to 8 bits each. For that, we need to understand a bit more on the hexadecimal notation of numbers. When we have a number between 0 and 9, we can represent that at 0 to 9 hexadecimal notation, and with 4 bits of binary notations. For example, a 4 is 0 times 1 plus 0 times 2 plus 1 times 4. A 9 is 1 times 1 and 1 times 8. Those that are above 9, namely 10 to 15, could be represented by a letter, A to F, whereby 14 is represented by E, which is 2 plus 4 plus 8. total of 14. The classless addressing introduced a concept of a mask. This mask allowed us to specify the shared bits of those octets without confining us to a boundary of 8, 16, or 24. We could use a 24 boundary like here, but we could also use another number, 23, 25, etc. The boundary was named by those consecutive ones. We could not set 8 ones, then a 0, then 8 ones, etc. They have to be consecutive so that a 24 ones is a legitimate mask, specifying the left side as the network address and the right side as the host which is connected to that address. Let's see a simple demonstration of the classless with 24 boundary, much like the C option. If we have an address of 192.168.1.4 and we impose a mask of 24 bits, we basically can compute the network address by multiplication using the AND logic connection between the IP and the mask. 0 and 1 is 0, 1 and 1 is 1. In that perspective, we can reach an address of 192.168.1 and 0 for the network. And the net address, basically the host, is given by the remainder, which is 4. We can generalize that also to non-fixed boundaries like 30. 30 means that basically we are sharing 30 left bits, giving only 2 bits to be the differing criteria for the hosts that are basically situated in that network. Given an example of 36, 24, 212, 27, we are representing that in a binary notation and imposing a mask of 31s. Performing an AND logic operation, we would receive an IP address of 36.24.212.24, achieved by the full 36 as above because these are all ones. Same here with 24 and 212. But here only 6 ones are taking a portion of the 27. That portion takes only the 16 and the 8 for a total of 24. The network address, which is shared by all members of the same network, is 36, 24, 212, 24 over 30. While the host that is stated within this framework is marked as 3. The remaining bits marked as 1 and 1. We achieve that by the operation of AND NOT mask. We're taking the mask, we're imposing one's complement over it, reaching only those 2 bits turn on, and when ending that with the IP, we would get only those 2 bits lit up with a 3. We can also identify a very important attribute called broadcast. When we want to send a message on layer 3 to all devices in the distant layer, we can reach that with a broadcast message, assuming that we have, let's say, a router that distinguishes our local network with another network, and we want all the devices in that other network to receive that message. If it was our network, we could definitely use broadcast on layer 2, but now we want to reach a distant network, and that can only be achieved on layer 3 and above. Using broadcast of layer 3 would guide the message to all the devices within that network that is shared by this IP network of 3624.1224/30. To do that, we're using operation of OR not mask, doing one's complement on the mask and ORing that so that all 36 here is achieved by the OR, the 24/12 as such, and here we're taking the zeros or the 16 and 8, as well as the other 3 which are turned by these 1 and 1, reaching a 27. This is very interesting because we are currently understanding that 3624.1227/30 is actually not a host IP address, but a broadcast one. Sending a message to 3624.1227/30 means that all devices within that network, this network, would receive that message. What does it mean over 30? Over 30 is something which is imposed by the router itself. When the router receives this 3624.1227, it imposes its mask over that address to obtain the host number that would receive that. If this host is basically a broadcast specification, all masks will get it. And if it's a specific idea, as we saw before, then only that host would receive it. Let's do 2 small examples. The first one is an 8-bit boundary example of 24. What is the network ID, the host, and the broadcast address? The answer is that if we're using that IP with 24, the left octets that are shared are 192.168.4.0, and the host, which is stated on that local area network, is 10. The broadcast address maximizes the right octet to achieve 192.168.4.255. This message sending to 192.168.4.255 will reach all the devices within that network. When we're using this address within 29 mask, we'll reach a different answer. The answer would be that 192.168.4 is achieved whatsoever, but we're also taking 5 bits out of the right octet. 10 is essentially 8 plus 2. That means that the 4 right bits are turned on, the second bit from the right and the 4th bit from the right. That means that taking 5 bits, that means 4 on the left and right on the right, 1 on the right, would only take the 8 value, and therefore this is the network address. Only taking this value within the network mask. The computer which is hosted within this distant network is number 2, led by the 2 plus 8, the 2 bit which is stated here. This 2 is specifying that the computer is the number 2 within this framework. And the broadcast address would be obtained by having all those 3 bits lit within this address, meaning 192.168.4, and the combination of 3 bits here with an 8. That's 7 with an 8. That's 15. We can easily compute that using some websites, for example, this calculator, or a Python, let's say, a program. We have to understand what broadcast is all about. Broadcast could be a specification like we saw before, 192.168.10.15, which specifies go to that network address and send to all its neighboring computers. That is very valid. But what about sending a message to that address, specifically saying send it to all the components of the world? Of course, this is not legal, and it would be dropped by all routers receiving that, with one exception, a DHCP message that we'll see in a minute. The directed broadcast, which addresses that network broadcast address we saw before, is legitimate, sending it to all its computers. The DHCP presents an issue. DHCP, Dynamic Host Configuration Protocol, is a protocol to obtain an IP from a bank of computers. There's a problem because when we obtain a new IP, we don't have an IP already. We don't know anything about, not to mention the mask or the router IP, nothing. Therefore, we're sending a broadcast message on level 3 saying, please help me out. It's not that we want to send it to all the machines in the world, just saying we don't know anything about IPs. Whoever sees that message, help me out. It's a message on level, let's say, 3 and above, and therefore must specify an IP and not a. I hope you enjoyed this video on IP addressing, one of the 26 lectures on the third course, TCP/IP and beyond, now offered on an attractive promotion in Udemy. Enjoy!